In this video, we will introduce how to construct the computational graph in the D0. So this is a basic block of the computational graph. We have a couple of input variable, and we have a function, and the function will take those input variables and do some calculation here and output a value to generate an output variable. So in the forward pass, the function will take the value from the input variable and output the value to the output variable. But in the backpropagation phase, the data will flow from the output variable toward the input variable. So that in the computational graph, we need to construct two sets of computational links. First is for forward pass. In the forward pass, the data will flow from here. We need a directed graph from the input variable flow to the backward variable. But in the backward phase, it will from the output to the input. So that we need to have two sets of links in the computational graph, so that we will be able to do both the forward link and the backward link. So here is the implementation of the variable and the function in the D0. First, we look at the variable class. There's three methods here: the constructor and the backward function. There's the extra set creator function. This is used to build the backward links. So we will explain how this is done later. But first of all, we check the forward pass first. By using the variable here, okay, you will see we have three the attributes for the variable class. The data will hold the value of the variable, and the grade is the gradient of this variable, which will be calculated in the backward pass. And the creator is a linked list, which will point to the function which produce those variable. If this variable is an input variable, the creator will be none. Okay, so we will see how this is constructed in the functions class. So in the function class, there is no constructor. Typically, there is no constructor, but we need to define a forward function and a backward function, which will be used in the forward pass and the backward pass. And in addition, we will have a call function. So we can input some kind of the variables into a function, and the function should return the output variable. So in this function, we actually, you can look at this. We actually take the input value from the input data, and then we feed this value into the forward function of the forward method of the function class, so that if the forward function should return the calculation defined in this function class, and we produce a value y here. Then we need to convert the value y into a variable, which will be the output variable of this function. So it's very important that any input or output, the of the forward function should be a variable, so that we could build a linked list between those variables. So that's a really important thing. So because if the y is a constant, for example, if we input the x into the y directly, and if the y is a constant, we will not be able to build a link. So in the function call here, we are not actually doing the mathematical calculation. Instead, we will try to build the computational graph as well. Of course, we still perform the calculation defined by the function. For example, if this is a sine function, we are doing the sine, calculate the sine, or if the function is s squared, we will do the s squared. But in addition to the calculation, we need to build the computational graph as well. So the way we build the computational graph is that, okay, for each function, we will connect to some input variables, and it will output to some output variables as well. Okay, so the input and output, if we check the function here, those two variables will be the input of the function. So we'll keep track of the input here, and then we will output to a variable. So the output attribute will point to the output variable. Okay, so we'll see that we're using the input and output to build the computational graph for the forward path. And for the backward path, we actually rely on the set creator function here. So when we have after the forward path, we get the value y, and we convert the y into the output variables, and then we will call the set creator of the output variable. So that, and actually the set creator method is simply point the creator to the function here, and in the function class, we are actually send itself to the set creator function, so that the output variable will actually point back to the function which created the variable. So by this way, we control the other path, so that we can go back from the output variable back to the function. So this link is not exist in the forward path, in the linked list of the forward path. Okay, so and for the function class, we need to define both the forward function and the backward function. So for the forward function, using to define the formula for the function class, and the backward actually calculate the derivatives of the functions. So for example, we can define a square function like this, and we only need to define the forward and the backward functions, the method. In the forward method, it take the input x, and we just write the expression in this way, and we can return y here. But we must be careful about look at this statement. It looks like a mathematical expression, but actually this expression will construct a computational graph instead of just do the calculation. And we will see how this is done in the next part of the video. But for now, you just need to know that we can write any mathematical expression here by using the variables or the function. We need to be careful that the x, both x and the y here is not a single variable. It's a variable defined by this class. So it's an object instance of a variable class here. Okay, so this why we can the framework can construct the computational graph, since those are objects instead of a simple value. And in the backward function, we need to do the calculation to calculate the derivative of the function. For example, this is x squared, and the derivative of the x squared is actually 2x here. And then we take the value from the upstream here by using the chain rule. So we just multiply those two together. So if you remember, in the last video we introduced how to using the chain rule to do the calculation. Here is the implementation of it. We take a value from the upstream, and by using the upstream and to multiply by the derivative of this function, so we can get the full value of the derivative against the output variables, the final output variable, or the in the deep learning framework, it's the loss function of the model. By using this way, we can get the gradients of the function, and then we can just return the gradient here. And then if we look at the backward function here, so for the backward function of the variable, you will actually take the output function, the function which created it, which is, for example, in this one, when we want call the backward of this variable, it actually take the function which generated it and pass the value to the functions per backward method. And in the backward method of that function, you will take the value, because the value, the grade in this variable it is the, because if we have other computer graph after the variable, it's actually the gradient to this point. So by using a chain rule, we can split the derivative against this function to be the gradient of this one to multiply by the gradient of this function. So we don't really need to do all the derivatives of this function against the final loss function, but we can reuse the value has been calculated, and using the value to calculate the functions, the derivative of the input variable here, so that you can take a look at that here. If f is not none, if f is none, it means that this variable is an input variable, so we just stop here. But f is not none, it means that this variable is produced by another function. So we just take the input of these functions, which will be those two variables here, and then we call the f dot backward, which is which should return the derivatives of this function no block, and we will send the self dot grad to these functions, so that when these functions calculate the derivatives, you only need to calculate the derivatives of itself, and so that we can use in the chain rule to reuse the gradient of a previous variable so far to do the calculation, and then we set the function to the input variable of this function. So we just display the gradient to the input of the function. Then we call the backward of the variable again, so that you will propagate the gradient toward from the output variable toward the input variable. So the value will be forward to propagate from the end of the graph to the start of the graph gradually. So that's a very efficient way to do the gradient calculation. It is not only simplify the calculation, but also making the calculation of gradients in a very complex function be possible. Because if you want to have a formula with every nodes in the calculation in the neural network, it will be an impossible job, because the calculation of the formula is very complex. It's not easy to do it correctly. So that by using the auto differentiation to do the job is a better choice. So in this way, we don't need to get the formula for each variable. We just using the chain rule to simplify the calculation. That will be easier to implement, and it will be easier to make sure the calculation is correct as well. We can use in so after this is the ESP function. So you will see that it's very similar to the square above. We take an input variable and do the calculation here to get the ESP of the input variable to produce an output variable y and return it. And then we using in the backward method, we get the upstream gradients, and then we do the calculation of the directives. The derivative of the ESP is ESP itself. So we simply put the same ESP function here and produce an output variable and then return it. Okay. So here is an example of the you can call it a model, or you can call it just an computational graph. So we construct an input variable, and whose value is 0.5 here, and then this is x. So actually, this we just construct an one-dimensional vector with one value inside it. But actually, we can have multiple value here as well. So in this case, S will become a vector. But almost everything here is the same. We will see later that we can introduce the vector and the matrix directives into the deep learning frameworks, and the only thing we need to do is that we need to make sure the shape of those the directive is correct. So we will discuss that later. But for now, you can just think this is just a variable. So we input this variable into the function A and return an output variable A, and then we put the A into another function, and we produce B, and we produce B into a function, produce Y. We can take a look at the the computational graph and the backward calculation in the previous video. So this is the forward path. So the forward path is exactly the one here, and the calculation of backward path is actually this line. Okay, so when we want to do a dy over dy, so it will be the one here, and so when we want to calculate the dy over db, so that in order to calculate this one, we need to know the value of the derivative against the c by using a variable b here, and then we just multiply these two to become the value of dy over db, and then this value will be input to this function block to call the backward method of the b, which will be actually used to calculate the dy of dA here, and the dy of dA will be the value of the upstream gradient, and to multiply the derivative against the function of b by using the value of a here. So we just multiply these two together to become the value of dy over dA, and then we can do the same thing for dy over ds as well. So that's the basics of the way we do the backward propagation to calculate the derivatives of all the variables in the computational graph. So actually this will construct in computational graph. Okay, the computational graph will look exact in this way. The x enter the function of a, and the a will produce all the circle is a function, and all the square here is a variable. So the variable x enter the function a, and then function a will produce an output variable a here, and then this variable will be input of the function b and produce the b, and the b will input the function c and produce y. So this link will be a computational graph, and then in fact the link here, the arrow here is the derivative graph of the forward path. And then in here we will call the backward function for the output variable y. This y is the last output variable in the graph, so that we can just call the backward function of the y, and we will calculate the gradients starting from the last variable toward the first variable. So therefore we call it backward here. You will actually call the backward method of the function c, and the result will be stored in the variable b here, and then the backward function of b will be called, and it will be called the backward function of b. So we will call this way toward the input variable. So after we finish the whole calculation, we will get the derivatives or gradients of all the variables here. Okay, so let's try to do the calculation by hand, so that you will be able to be more familiar with the whole procedure. So before we do the backward pass, we need to do the forward pass first. So in here we know that the input value of x is 0.5, so we just store the 0.5 here. This is actually the data attribute of the variable. So the data variable will be the 0.5 here, and then we call the forward function of the of the A, which take the X as the input. And then in the forward pass, in the forward pass, we will implement the function of A, and the function of A is a square here. Okay, so 0.5 square is the 0.25. So the value will be set to the value of the data of the variable A, so which will be the 0.25, and then this variable will be input into a function B, and the B is an ESP function. Okay, so the ESP function 0.25 e power over 0.25 will be 1.28, and so the function B will produce an output variable and save the function inside the B. So it's 1.28 here, and then you will call this variable will send to the function C, and the function C is an square as well. So the square of 1.28 will be 1.64. So this will be a value of the final variables y here. So in this way, we finish the forward pass of the computational graph, and we can change the value of the input variable, and the same calculation will be do again by using the same computational graph. So in the whole calculation, the computational graph will be controlled for once only. Once the computational graph is constructed, we can using different input variable and do the calculation for each different input. Actually, in the deep learning training, we may have millions of the input samples, which will be assigned to the input variable here, and the forward function of this one will be forward through the whole computational graph to finish the calculation. Okay, so after the forward pass is done, we can call the backward function of the y, and you will start the backward propagation procedure, which will calculate the derivatives of all variables against the output of variable y. So this is done in this way. So first of all, we will set the gradient of y to be 1. So all you can see the node in this shape will be the gradient of y. So this is the data, and this is the grade, and this is the value of the attribute. So in the grade attribute of the y, we will say it to be the 1. The reason is that the partial y over partial y will be always 1 here. And then we want to calculate the partial y over partial b. So in here, we hope that we would calculate the partial y over partial b here. But how we can calculate it? We need to take the upstream gradient, which is 1 here, from this variable. And then we do the calculation of the function against the current value of the function b here, according to the c. So since c is a square function, so it will be 2x. And what's the x here? Is actually the the variable which is the value which is decided in the forward path. So the 1.28 will be here. We will using the value of a variable b. So that in this way we can get the value of partial y over partial b. Since this partial y over partial is equal to the partial y of partial y dot partial b of partial y. Okay, so this is actually this term is the gradient of the previous layer, so which is 1 here, and this one is the gradient of this function, so which is 2x, with 2x here. So we can use in this way to get the directives of the y against the variable b here. Okay, so we can repeat the same procedure for the variable a here as well. So this value will be input to the will call the backward method of the function b, which is the ESP function, and then so that again we will get the upstream gradient here, and then we can calculate the derivative of this function by using the value of its input variable, which is a here, so that it will be the ESP 0.25, and the value will be 3.29. So this will be set to the grade attribute of the variable a here, and then we will call the backward function of a again. So the procedure will be again. So this is upstream gradients, and then since the a is x squared, so we will have the 2x here by using the values in its input variable again, and then we got the final value, which is 3.29. So in this case, we calculate the gradient of every functions. Okay, and in a deep learning training we will discuss later, we will actually using those gradients to change the parameters in the function, so that those function, this computational graph will produce a better result right here, which will be closer, more close to our ground truth. Okay, so this is the way we do the calculation for the backpropagation. So I encourage everybody to do this calculation by hand, by yourself, so that you will be more familiar with why the backpropagation is implemented in this way, and how the auto differentiation will be implemented, and why the auto differentiation is better than using the normal directives. And actually we can for the calculation of the gradients, we can do it in the forward way instead of backward way. But if we do it in the forward way, we cannot just using the derivatives of the function itself. We need to consider all the calculation after this one. So it will be much complex than doing it by using the backward way. Okay, so in the next video I will try to introduce how to make the implementation of the computational graph to be more intuitive. Because we leave some question here without the explain. In here, we using for example in this one, we just using the x square here. This look like a mathematical expression. Why this will become an computational graph? This question will be answered in the next video.